Hello everyone, and welcome to the Shear Testing Lab. For this lab, we'll be having you perform a series of tests designed to assess the behavior of a set of materials under shear loading. We previously tested samples in tension to learn a bit about axial stress, axial strain, and the modulus of elasticity for each material. This lab, we'll be looking at shear stress, shear strain, and the shear modulus, and comparing them to our previous experiment. As a reminder, shear stress occurs when a force is applied tangentially to the cross-section of a component. This creates a shearing action. If we consider a fixed block of height h and area A, we can apply a tangential force to the upper surface, resulting in some horizontal displacement delta x. We can define our shear stress, tau, as the ratio of tangential force over the cross-sectional area it's acting on. Our shear strain, gamma, is defined as the delta x divided by the height of the material that we're working with. And our shear modulus G is tau over gamma, the same way we would do our Young's modulus. To compare a Young's modulus and shear modulus, we use the Poisson's ratio, or the lateral over longitudinal strain. For this lab, we'll be attempting to experimentally identify the difference between shear and tensile loading, determine the shear modulus for a given set of samples, and determine the Poisson's ratio for those same samples.
For today, you'll be provided a series of samples. Using these samples, we'll be performing the test using the same camera and tensile setup that you used in the last class.
Last lab, you were provided a set of dog bone samples for tensile testing loads. This lab, we'll be using a modified ASTM B831 sample for testing shear. The shape of the sample is a little different. It gives us a single shear zone in the center, which gives us a simple geometry to work with. This central area can be modeled as a small block experiencing shear, all without changing our apparatus setup.
To get started, what you're going to need to do is come in and load your sample into your machine. Today, I'm going to be starting with the sample we used from before, which is just a stainless steel sample, and I will load it in just as we did in the last class. My goal for this sample, I can rotate these jaws just a little bit. Thank you, Victor. My goal for this sample is to capture specifically the interior line right here. That's where the shear sample is going to be measured. Once my sample is in place, I'll apply a small amount of preload, hopefully in the right direction. Only about 5 pounds also, we don't want to go too high. I will zero my sensor, and I will actually make sure that my dial indicator is properly aligned. Once this is in place, I'll then go to setting up my camera.
To get started, we'll set up a blank project. Once the software loads, our goal is to set up our first camera. Ideally, we want to get as close to the center of the sample as possible and get the cleanest and sharpest image we can manage. I'll start by initializing the sensor. As you can see right now, I'm not really focused, so I'll bring the sensor down a little bit, and I'll actually use the arm that it's mounted to bring it into alignment. It's okay to move the apparatus and the camera as much as you need to get the best shot you can. To adjust the exposure or the focus, there are 2 rings on the lens of the camera. Once the camera is in place and you're satisfied with its position, you can turn these to increase or decrease the brightness or sharpen the focus depending on what you're trying to accomplish. For right now, I've got this sample a little far out. You don't want to be a little closer than I have it right here. But for the purposes of demonstration, this should give you a pretty good idea of what you're looking for. Avoid the sample having any red dots or striations. This indicates that the sample is actually washed out and we're actually not getting a good result. Once the sample is aligned and you're happy with your setup, what you're going to want to do is set up your acquisition. To set up acquisition, our goal is to choose both a frame rate and a total image count. Our frame rate represents the number of samples per second we're going to try for. In this case, I have 12 Hz. I recommend raising this as high as you can. Somewhere around 20 is ideal, but not all computers are currently supporting that. Once I have that value, I'll choose the total number of images that corresponds to the number of frames per second I want. In this case, 100 frames gives me about 10 seconds of total data collection. At this point, if I hit the OK button, the samples will begin to collect. So I'm going to hold off on that right now while I prep to record the rest of my sample.
Now that the system is set up and are ready to perform data acquisition, you're going to want to break your group up into 3 people. 1 person to man the computer, 1 person to record the displacement as well as the force, and 1 person to turn the crank. These samples are much thicker than the samples we used in our prior labs. With that in mind, please make sure to not go over 150 pounds. Ideally, we'd like to keep it around 125. These samples are so thick that the poundage will actually increase relatively quickly, so I want you to be careful. Turn the crank very, very slowly. Remember, the number of frames you're receiving and the hertz that you're recording at is the total amount of sample time you want to take in order to actually gather your data. All right, we'll zero that back out, zero this back out, jump back in there.
It's at this point that I should probably admit that, unfortunately, we forgot to hit record on GOM Correlate. Please make sure that you do that properly, and don't make the mistake that we made. As long as you have all three data sets, you should have all the information you need in order to identify the shear stress, shear strain, and shear modulus of your material. If you've collected all of your data correctly, for each sample you should have three data sets. First, a set of displacement data. Second, a set of force data. And third, a set of data from GOM Correlate, or GOM Snap, For this lab, we're going to break the analysis into three parts. The first, and probably the simplest, is going to be to take your force and displacement data and generate a series of plots for shear stress versus shear strain. Using these plots, you'll be able to identify the shear modulus of the material. We want you to take that shear modulus and provide us with some commentary about why it does or does not match the existing records or literature for the shear moduli for stainless steel and copper. Once you've completed that, the second analysis will be performed in GOM Correlate. In VLabs, you'll use the software and the above tutorial to determine the strain in both samples. You'll be looking for the longitudinal and axial strains, which we can compare to give ourselves the Poisson's ratio. For both samples, identify and isolate the Poisson's ratio and compare it again to a literature value. Let us know why or why not your numbers match. Finally, using the tensile test data from our first lab, you'll perform the same experiment in GOM Correlate to identify the Poisson's ratio for each material. Do the results for these fall into your expectations? Let us know again why or why not. The deliverable for this lab is a PowerPoint, so make sure to get lots of good pictures from GOM Correlate to explain what data you're seeing. And also, make sure to take the time to understand your results. Remember, our goal here is to understand shear, not just to gather data. Give us commentary on where you think this can be used, and give us context for why you think this might be important. If you have any questions, feel free to ask your TAs, myself, or any of the learning instructors who are walking around during your lab, and we'll be happy to help you. Good luck with your lab.